All right, so it's March 18th, 2024, and I am Hanson Su, here with Eric Horvitz. So, can we start by introducing yourself?
I'm Eric Horvitz. I'm Microsoft's Chief Scientific Officer.
And tell us how you first got into artificial intelligence.
I became deeply interested in the brain and mind as an undergraduate. I was doing a biophysics undergraduate degree, and I was getting excited about biology and also chemistry and physics and bringing them together. When I ended up in a neurobiology laboratory doing research and was completely blown away when listening into single neurons in rats' brains with a single microelectrode. And I was intrigued looking at the oscilloscope. I remember these moments where the questions arose, how on earth did even 1 trillion of these or 100 trillion of these little mechanisms add up to minds of the form that comprise my own mind and experience. And as I set off to do an MD PhD degree at Stanford, transitioning into the world of computing from biology with my graduate program, I moved over to MD PhD in artificial intelligence at that time.
Oh, thank you. And can you summarize for our museum-going audience your major contributions in the field?
I've been fascinated by methods for relatively simple agents like humans immersed in a complex universe to do well. This idea of bounded rationality. My contributions in artificial intelligence include the notion of how do you build systems that can grapple with uncertainty, make decisions with limited time and information that are bounded rational, but where we have a theory or principles of intelligence you would need for any level of intelligence for how you do well in complex worlds, in the open world. That research was framed in a way by my interest in applying artificial intelligence in medicine, which is a high stakes area. You want to make sure you're doing the best you can, even under limited time. So in my doctoral work, I was looking carefully at what does it mean to have a system helping a physician while a patient is gasping for breath and you have limited time and the system can't necessarily solve the whole problem. Can it be as helpful as it can? And that led to a theory or a set of principles and prototypes. Later on at Microsoft, I was deeply interested in applying these ideas to human AI interaction or collaboration, building dialogue systems that could work with a human or more than one human in conversations, building systems that could augment human intelligence by understanding the complementarity, where people were strong and machines were weak and vice versa, to come forward at the right time in a dance we call a mix of initiatives, computer or AI helping versus the human working on a task together, who goes when, and how do you contribute in a way as the AI system to have an ideal collaboration. Other ideas included taking core notions of probability theory and decision theory, which I was very focused on in terms of building various models that run in the real world and applying them in systems that could predict outcomes in healthcare, like readmissions. When I first started working in the field of AI, the department I was immersed in was excited about using rule-based expert system technologies. This is logic-based. If A and B, then C. What I and a couple of colleagues started looking at very carefully for the contributions is re-aiming the field of AI into the statistical realm. one where there's uncertainty and there are probabilities and there's costs and benefits under uncertainty. And in moving from a logic world, which was quite limited for doing, I think, open world reasoning, like for healthcare, for example, we have complex symptoms and physiologies, into probability, it gave us a new approach or a fresh approach to thinking deeply about building systems that could do well in the open world. Now, probability and decision theory, actually building systems that could actually predict the future and that could diagnose or recognize patterns under uncertainty, was also quite challenging. And that brought me into looking at principles of bounded rationality. If a doctor didn't have enough time to think, given a patient's gasping and the system is trying to help under the same time pressure, how could a system do well even with limited time and information? This led to principles of what I would call bounded rationality, which I think are important for as general principles of intelligence to be applied in many different ways. At Microsoft, I worked on teams to do the earliest work on AI at Microsoft. The spam filter we all depend on now was a probabilistic system we had built. I started looking at human AI collaboration as a grand challenge for how AI systems work with people in the open world. Dialogue systems, systems that could converse with human beings in a back and forth, in a fluid conversation, were a focus of attention. Systems that could augment human intelligence by understanding the complementarity. What were people good at, not so good at? When should they come forward? How do you control the mix of initiatives between AI systems and humans when they work on a project together?
Thank you. I want to hone in on something you just mentioned. So you mentioned statistics and probability in AI. Can you talk about how the emergence of the World Wide Web affected the growth of statistics and probability in AI?
In many ways, where we are today comes at a confluence of several factors that have kind of led to this moment, ignited this moment in certain ways. First of all, the world of machine learning from data to do tasks, to do predictions, to generate plans. There was very little data around. Now, when I was a grad student at Stanford, I remember taking a fairly big chunk of my fellowship for a quarter and buying this incredible new thing, a hard drive, a 40 megabyte hard drive. And it was this enormous store for me of data and pictures and content and my dissertation. And I remember when that crashed, I lost 40 megabytes, and I just was scrapping around, like, how do you live without my 40 megabytes? Here right now in my pocket is probably a couple of gigs. On my phone is a few gigs. It's a different world. We couldn't even store data effectively until the late 80s to even have databases to learn from. The World Wide Web gave us enormous quantities of data of the form of human consumer behavioral data, but also became a place for digitization more generally, transactions, building large corpora of content. Wikipedia, for example. And I think that the data sets that have come from, first of all, being able to store data, and secondly, the flows of data and the digitalization of our society have provided enormous quantities of data which have been required as basic fuel for modern artificial intelligence research.
Thank you. Can you talk about how much search has affected machine learning, the use of machine learning or research into machine learning?
Well, when I came to Microsoft, the goal of our team, we were the first artificial intelligence research group at Microsoft in the early 90s, was to look at many places where AI might be applied. And we applied it in many different places, in systems that could generate help in office applications, productivity applications, for example, spam filters, ways to prioritize your emails so you knew which email was the most urgent to look at right away, which emails would get sent to you on your early cell phones when it costs quite a bit to send each message to someone's mobile device. Exploring ways to even make the operating system work better. Even today, Windows is always doing machine learning in the background, guessing what you're going to do next and predicting that and sort of getting things ready so it seems even faster and more efficient than it would otherwise do memory management with probability theory and decision theory. Search was a critical application that came with the growth of the web. This idea of having an index that you could go to aged out very quickly, and the world needed tools to help people express in natural language what they wanted very quickly in a way that systems can understand and ground with, and then go out and provide the right links and pages back to that person, best ones to address their information needs. Machine learning became central at Microsoft as the approach for indexing and retrieval, both in designing our algorithms, in thinking through the commerce aspects of search, advertising, matching appropriately, understanding how to fold in context, which became very, very critical in our work at Bing, to understand how to personalize search over time. So we can say that that getting people amidst a gigantic sea of data the right knowledge they wanted, given a very short query, was a grand machine learning challenge.
Thank you. And could you talk about, actually, I want to go back to a lot of the things that you mentioned that Microsoft did in AI. What were the sort of the timeline, like 90s, 2000s, 2010s? Like lay out maybe sort of which things were developed at what time?
Well, I came to Microsoft when our Stanford University grad school era startup was acquired by Microsoft. We were working back then on probabilistic methods using probability theory to do medical diagnosis. Our startup expanded that work into diagnosing failures in jet engines, working with United Airlines here in San Francisco, taking our methods down to Mission Control Center at Houston Johnson Space Center to diagnose from streams of events coming out of the space shuttle sensors what was happening on the shuttle. Was there an error or failure?
Mm-hmm. What year was that?
That was in the late 80s, and I came to Microsoft in 1992. We made our sort of deal with Microsoft to come up and have our company and assets acquired to take the mission forward. At that time, I was very much excited to hear that Nathan Myhrvold and Bill Gates wanted us to take this probabilistic approach, these statistical methods of AI, which were still new and evolving very quickly, and they're the foundations of where we are today, into all of Microsoft's products and services. And that was quite a carte blanche to just come up and move and take our technologies out into the world. I remember in negotiating to come to Microsoft, I was thinking, yeah, I like this idea of our startup, and we're growing our startup in Palo Alto, over here on California Avenue, versus joining a bigger company with an uncertain future that had a popular word processor and Windows 3.0. And then talking to Nathan Myhrvold, who was the chief advisor in technology to Bill Gates. And as he talked about the possibilities, especially with AI in all the products, I remember picturing this lever with the fulcrum at the horizon. Can we take our ideas into this larger company and leverage the company to push our ideas, which we thought would be very useful for the world, into an array of products and services? So around 95, we had built a probabilistic health diagnostic system that was fielded on MSN, one of the earliest applications on Microsoft Network, that did diagnosis for pediatric care in pregnancy. We had numerous projects on troubleshooters, so we had probabilistic AI running print troubleshooting and troubleshooting your Excel spreadsheet back in the mid to late 90s. Around 1998 or so, we started fielding applications that were leveraging email as the general workspace for so many people. I was excited about several things in AI in electronic mail. One was, could we understand using natural language processing, which was another focus of attention at Microsoft Research, plus the probabilistic statistical approach, what people were trying to do in email. Were they trying to schedule a meeting? Could we automate that? Could we have experiences where you could just talk to your system and have an assistant working with you, demonstrating how one day you'd work like with an automated assistant that could help schedule by understanding your email and understanding how to work Outlook. That was the Lookout project. Then I got very excited about, and I took ideas that came out of my dissertation work on trauma care and emergency medicine. And instead of thinking about each patient, now we were scaling things up to hundreds of email messages, where an email message had a certain time criticality, and it needed to get attention. Taking these ideas to email gave us the priority system, which all of a sudden gave us this beautiful approach to using machine learning by watching you work with email to alert you about the highest priority email messages coming in. And of course, at the same time, we said, you don't want to, we saw a rise of spam or junk email and wanted to filter that out. So we worked on the email prioritization and email filtering in the late 90s and began to field those technologies. Also get very excited about this long-term approach to applying these principles of limited resources and bounded rationality to the operating system, to Windows. And in several efforts, we started looking at, can the operating system itself know how to personalize itself to each user by watching their sequences, understanding when they were going to do what, predicting their next move, and staying ahead of the actions so we could pre-compute, giving more power to systems virtually. Then came the rise of the web, in the 90s, and throughout became a theme of how can we do better search and retrieval with AI. Then came the whole ad marketplace. How can we make that work better over time? Then there was translation. Could we translate between languages? How could we sort of generalize these powers we were providing beyond English? And started having some wins in translation, starting around probably 2002 or so with our translation work. The big upswing in AI that the inflection we're riding right now, I would refer to as the neural network models inflection, with a methodology called deep neural nets or deep learning, of using basically an older technology called perceptrons from the 1950s and 60s, revisiting the method with new kinds of approaches like many levels. New methods weren't that new actually, but methods that had been proposed years earlier, one called backward propagation using gradient descent. Methods that came out of the late 80s and early 90s, being now applied for the first time with new powers of computation and a lot more data, and seeing translation lighting up and other technologies lighting up. So along the way, there have been these key moments. In 2012, a key moment was when we just barely got running, not just translation, but real-time speech-to-speech translation, where, for the demo that we did in Tianjin, China, Rick Rashid, our research director, in front of an audience, in a demonstration we weren't quite sure would work. It just barely was held together by, as they say, baling wire. and chewing gum. But we were in front of a big stage of graduate students in Tianjin, Chinese graduate students, and Rick started talking, and we wanted to demonstrate in his own voice, speaking back in Mandarin, in a volley with his own utterances, having the AI system do that fluid translation, showing where the Star Trek future might go with the universal translator, as we often refer to this project. And to have that actually work after a stutter, you can still go to the web and see that demonstration. I filmed it. Actually, I brought my camera up. And I remember turning around and I saw a young Chinese graduate student taking her translating piece off her ear with kind of a tear in her eye, listening to Rick talking in Mandarin. And those moments were enabled over time by the progression of the AI technologies.
Mm-hmm. I want to go back to, you mentioned, early 2000s, Microsoft was already doing translation.
Oh, yeah.
Could you talk more about that and the methods that were used there?
So, two of the earliest groups at Microsoft Research, which kicked off in 1991, and our team kind of arrived in 1992, were our team, which has got a core AI, artificial intelligence, and natural language processing, the NLP group. Translation started out being a task centered in our natural language processing area, with help coming from other teams, including speech recognition group, the AI group, and others. And around 2001 or so, we started an effort to see how well we can do with translation, and assembled a team that started focusing in that realm. Around the same time, natural language processing itself was going from a logic-based methodology with rules of grammar and so on, and linguistic rules, into a statistical methodology. We ended up building statistical natural language processing methods that turned out to be very helpful in building translation systems, starting out with systems that would be trained on large quantities of aligned text. You can find such text, but it was, in general, pretty challenging. Like, turns out that for the Canadian Parliament, they systematically have English and French aligned. What a great training set for a English-French translation system. Those kinds of corpora were used and leveraged early on. Around 2001, around 2006, 2007, 2008, we started getting to the point of getting more competent. But big changes started happening around 2009, 2010, with now bringing in the deep neural modeling technologies.
And so was, with the entrance of deep learning, was that did that come in with Li Deng and working with Jeff Hinton?
So it's a really interesting story about Jeff and I. I visited Toronto, the University of Toronto, in 2005 after being off on sabbatical. I had a 2-month sabbatical where I was in the Azores Islands visiting some of my wife's family and with her and my son. And I got back and I was kind of like a little exhausted and probably not my normal kind self. And at Toronto, after I gave my keynote lecture, you have a day of meeting professors, and I came to see Jeff Hinton in his office, and he was being very excited about what he called back then deep belief networks, and we were talking about these, and at some point I was getting tired, and I said, Jeff, very few people know what you're talking about in the field. You're always so excited. I'll tell you what I'm going to do. I'm going to go back to Microsoft, and the very first thing I'm going to do, coming back from my sabbatical on Monday, this was a Friday, will be I'm writing you a check, and that check will be a donation just to you, and you have to promise me to spend every penny of that on explaining yourself. So Jeff wrote this beautiful paper which appeared in Science magazine, and our teams at Microsoft read that a couple of years later, maybe about 2007 or so. Read that and got excited about Jeff's work. We invited Jeff out to speak. Eventually, we invited him to come out for a summer with us, and that was 2009. And he came with a grad student, Abdul, and it was that summer that things were coming together in a way that we realized that this deep neural network approach that Jeff had been pursuing with passion for years, he never stopped. We knew him for many years. And that method was not favored. It was, traditional machine learning methods were doing better than the deep neural models. But that summer we recognized that the deep neural network method and the technology, the constellation of methods, was simply famished for computation and data all those years. And when we got them those raw resources of compute and data, we saw, in that case that summer, speech recognition lit up. We were applying the methods to a challenge problem called the switchboard data set, which was an interesting challenge problem in speech recognition that for a decade, even though people were hammering on this, couldn't get the word error recognition rate down. It kind of had plateaued. And that summer we saw a jump, like the needles jumped. We said, okay, something is very interesting here. By the way, the switchboard data set is interesting in that it was collected by, we'll say, an unnamed government agency with 3 letters that paid people to just talk on the phone, low bandwidth phone lines, just have conversations. I'm not so sure what they would do with that kind of capability, but that was the kind of the goal of that research challenge problem, and it was called the switchboard data set. But we saw a jump that summer, and we got very excited. Those results were published, led to a workshop, and then I think from there that was one of the sparks that led to the kind of the takeoff of the field.
Can you describe, given enough data and computation, how is deep learning different, and what makes it perform better than the previous machine learning methods?
A couple of things have happened, and you could say there are certain characteristics of the methodology and the approach, which is interesting. Part of it is discovery. We're discovering there's a natural science that we didn't understand before of how these large-scale systems operate. It's also new kinds of methods for training, for example. So several factors. One is that unlike traditional machine learning, the deep neural models tend to build their own representations rather than in the traditional approach where, let's say, for a medical diagnostic system, engineers will work with physicians and write down all the observations that might be seen, and then collect frames of data where it's like, okay, in this patient we saw these symptoms, and here was the final diagnosis. And we do that for 1,000 patients. These predefined, we'll call them features or attributes. With deep neural models, we point the system at the world, and we basically give it a challenge problem, and we ask the system to learn the representation internally on its own, sometimes hierarchically, starting at the bottom and then grouping these features together in a way over a tower where you end up with higher level representations, and these are all learned automatically. That's one difference, which gives us some power because it's not so handcrafted and relying on human expertise, which tends to look at a piece of the problem sometimes. Secondly, a couple of breakthroughs happened even over the last decade, 5 to 10 years. The current models that we're building and that we're excited about today, which might not be the same models we'll be excited about tomorrow, because the field is moving pretty quickly, are called transformer models. It refers to a particular architecture, but one of the interesting pieces of this architecture is that we ask the system, when it comes to looking at sequences like language, you figure out in predicting the next word what to look at on your own. Just look at the previous history and you learn what to look at. You learn the context yourself. In a way, it's like learning what to attend to, learning patterns of attention, which are also, it turns out to be a very powerful tool, and automating that over large corpora. And probably one of the more intriguing and interesting developments is called self-supervision. Now, the word supervision in machine learning has referred to a human typically supervising. In other words, saying, here's a patient, I'm going to label that Hodgkin's disease. The signal of labeling is called supervised learning. And supervised learning has been required for building tagged data sets that have all the information you need to know if you're going to train a system, because you have whatever the goal prediction is, or diagnosis is, or pattern or scene you're trying to, or object in a scene, labeled, and then you hide that label at test time. You give it a training time, and at test time you try to predict that missing label. With self-supervision, it's a very clever but simple idea that was invented just a few years back, where, let's say you're given all of digitized fiction, or all of the Wikipedia, and you tell the system you want to learn to just predict missing words. How do you do that? Well, instead of asking people for labels, which is very tedious and time-consuming and led to limited data sets that were cherished like diamonds coming out of a coal mine, now a system just randomly will hide words, plays hide and seek with words. Hide a word, try to predict it. Hide another word, try to predict it. You can do that billions and trillions of times and build understandings of how to predict missing words. And in certain transformers, you're just predicting the next word. And what's amazing about these methods, what we're seeing today, and there's still questions arising, and the top computer scientists are intrigued about this. Certainly, I'm excited and curious and very intrigued with how building systems to get better and better and better in sequences of predicting the next word or the next pixel. We can start to push them so hard to get better and better at that it seems to be building internal representations that are very rich and powerful. And we may even say that these systems are building world models as they're getting better at predicting. Models that put things together better than just statistics or patterns, but are building are compressions of the world, shadows of the world, representations of the world that have almost magical properties to seem to understand certain disciplines, to do new kinds of operations, like to specialize, to abstract, to generalize, to compose, to be polymathic, cross-disciplinary. So we're seeing some very exciting things today that I'd love to. I can't wait to see what comes next over the next decade.
Mm-hmm.
All right.
Okay, so we talked about the Microsoft's work in traditional machine learning, in search and advertising and translation. How large were those efforts?
Microsoft Research was about 100 people around 1995, 96, when we decided to triple the size of research and went to about 300 towards the late 90s. At that point, we started labs first in Cambridge, England, and then in Beijing, China, and started to grow those labs as well. And all of our labs would be contributing to our research on multiple fronts in artificial intelligence. It's hard to give exact numbers because we had teams working on different aspects of our projects. And when we stood up a bigger effort like machine translation, we would grow a group around that aspect. Also, as Microsoft matured Microsoft Research wasn't the only place, of course, that R&D occurred, even advanced R&D. We saw quite a bit of that, as we do today, across the whole company. So in standing up a search team around web opportunities, we had quite a bit of R&D and advanced R&D happening over in our product division as well. And at times we would transfer a whole team from Microsoft Research into a product division. So I can't give you exact numbers, but let me just say that over time, AI projects began to become more central at Microsoft. There was a grand vision that Bill Gates had imbued the company with, of someday having computer systems that could see, hear, read, and understand. And this mission pervades the company in many ways. So there's been a long-term interest in pushing at any moment at the frontiers of that technology, pushing it forward to see what could be done for actual customers in the world.
So we've talked about, the various eras that you've experienced in AI over your career. So expert systems, statistical machine learning, deep learning. What makes today's era of transformer models and generative AI different?
Yeah, so I've seen a number of, we'll call them paradigms in AI. And of course, when I got into the field, we studied even the earlier paradigms. And so AI started in its earliest days with a mix of statistics and logic-based methods. But then in the early 60s into the 70s, logic-based methods, systems that would reason, do theorem proving or theorem proving-like inference methods became quite dominant. And in fact, when I was in grad school getting interested in probability theory and its extension into decisions or decision theory, when I would bring this up with my advisors as something I was getting interested in, some would actually say in AI, well, you're showing signs of physics envy. The number-based methods aren't really AI. Numbers, we want to do symbols, symbolic reasoning. And I would always think, well, aren't numbers symbols too? And don't we need to sort of have uncertainty and probability? So you can almost see that many of the early works in research going on right at the cusp of the blossoming of statistical artificial intelligence was done by grad students. We had like an invisible college across the country. And in many places, our mentors weren't necessarily excited about what their grad students were doing and had to be sort of, gently taken along on the ride until the excitement would grow and we could persuade the more senior people in the field that this wasn't a throwback to operations research or stuff that wasn't AI. It could become central in AI to really think this through. And we first had statistical methods called Bayesian networks, also referred to with the generalization probabilistic graphical models. That was kind of based on assessments of probabilities, less via machine learning methods, because machine learning wasn't all that popular yet because data was scarce, I think, was one of the reasons. But then with the advent of data and compute available and methods for now learning these representations from scratch, these graphical models as they're called from scratch, we saw the rise of those methods and other methods in traditional machine learning. Boom, we had a paradigm. There was always this paradigm called connectionism, which lived side by side with what I would call mainstream AI as it evolved. And even in the 80s, there were debates between connectionists, as they were called, these neural net people who were always very interesting. And I was always intrigued with this group because, we know that the brain is kind of a connectionist model, but no one knows really what goes on in human minds and vertebrate brains more generally. But they were always kind of outsiders to the field. And so when, in the early 2000s, when deep neural nets, 2005, 2006, started showing power with computation and data, there was a new inflection of deep neural networks. And I mentioned 2005, 2007, 2009, we saw very fast-paced work. We were at an AI inflection. And my comment is on where we are today is we're seeing now with generative AI models, with these large foundation models, as we call them, an inflection upon an inflection. I almost see the curve. Inflection, deep learning. Applications, excitement, inflection again. And what we're seeing most recently that's quite different is we're seeing models that are, I think for the first time, behaving in ways that people would describe as showing glimmers of the way people think. I'm not making any comments as to what's going on behind the scenes being similar or not, but we're seeing systems that could generate language and imagery in a way that people do, that can converse coherently with people, seemingly in a fluid manner, in a coherent manner. This is very new. It's a very new experience. I mean, when ChatGPT was fielded at the end of November of 2022, the original idea was just to gather data with a prototype. But it exploded in terms of interest in use, in part because it was so easy to work with and mesh with humans. People found it just would flow with their dialogue, questions and answers, in a way that touched people in daily life more readily than AI systems had touched them in the past, whether it be a spam filter, yes, very useful, a medical diagnostic system, yes, we're going to see that the advent of those systems helping physicians. It's been a slow translation. Systems behind the scenes that we don't know about, like the prefetcher running in Windows operating system. All of a sudden, we had an explicit human-like experience with AI systems that would respond in ways that were delighting people and assisting them in numerous ways. So that's what's different about the current era. And scientifically, what's different is as AI researchers, we have questions where we're seeing where the empirical behavior of these systems, how they're behaving when we build them, is sometimes beyond expectation and understanding. So there's excitement in the mystery of what this path has uncovered, what we're seeing now in terms of lighting up more research in AI. What does this mean? There's this background question also of how does this relate to what goes on in minds? Are we discovering principles of intelligence of the form that biology may have discovered? We really can't make an assertion about that just yet, but it's certainly opening up questions.
Yeah, I'd like to push on that. So there's a current debate right now about whether or not large language models are actually understand language, or whether they're just stochastic parrots. They're just pure word predictors. Where do you fall on that?
First of all, it's understandable why people who have been in AI for a long time and have worked on rich symbolic approaches, or even approaches where there's clear machinery behind the semantics of language, for example, why they would look at this method, look at the excitement about these new approaches, and put their hand on their hip and say, yeah, but can it do that? Can it plan? Can it really understand what that word means or that phrase means? And my reaction is it's not so easy to give a clear answer, yes or no, to that, because it cuts to the foundation of what is meaning. Might it be the case that the way we understand words, like leave through the door, close the door, I'm getting hungry, come from rich contextual cues and experiences over time that can be codified as contextual uses of tokens or these concepts, amidst other concepts in large representations that imbue that specific word with meaning. It's certainly interesting to have these systems behave like they're behaving now with the competencies they're showing, whether superficial or deep, in framing the question about what does it mean to understand the meaning of a word. So I won't give you a direct answer, yes or no, but certainly these systems have gone beyond what you might call a simple stochastic process. Calling these systems just doing that may be akin to calling our own ascribing of meaning to words as being somehow statistical, given the context at hand and our shared understandings of how language is used.
Thank you. I want to go back to talking about the business models of...
That's so boring.
Okay. Gotta get this question in.
Okay.
So...
we're not there for that reason.
Sure. So how are large language models changing the way that users are seeking information, and how might they change the business model for serving ads in search?
Let me first say that a number of us are discovering, even researchers at Microsoft, per our own uses of the technologies, all this magic about how these systems can be used in a variety of ways in daily life, including for search and retrieval, but for other things. Like these days, will come in the morning, ask my M365 Copilot to help me with the mail that's come in that I haven't read yet. When I last heard from somebody, summarize mail, what action items have I not addressed yet? What commitments do I have that are unaddressed that I've made to others? Whose questions have I not answered yet? The power of these methods in daily life is really pretty impressive. On search, it's interesting. Just this week, I was searching for an old web page, as I recently mentioned to somebody, a web page I had built in the 20th century about an experience that I had had, and I was looking for this page in search. And as I was pulling the page up, because I just didn't know where I'd even had located it in my own web page tree, Copilot started writing a summary of the page to the right. And I said, that summary is better than my own page that I had written. I'm going to use this summary, and I'm going to basically send this summary out with the link as a way for somebody to sort of get the essence of what I had on that page when they had asked me for the whole page originally. And the fact that I was just looking for this page, and to the side, the system wrote out a beautiful summary. I was like, oh, this is even better. I'll take this, and I'll use this as the more essential package I want to send to this person for the information that I like to render. It's short, it's a great summary, and it's exactly what I was looking for. So how will how we retrieve information change over time? It's hard to know. I know in my family, I've watched my family members using without special prompting, or we're at Microsoft to try this out, using the Copilot, especially on mobile, quite a bit more than even regular search now. There's especially there's special energy in using it, especially because you can see quickly the references when you can see the sources being cited, and when the system is weaving together information from multiple sources in one place. In some ways, there's an opportunity to really, over time, and we can work on making this better over time, really custom tailor the answer to what the sensed need is, or even go back and forth and ground on the actual information goal of the end user, and craft an answer that pulls from many places, including the ability to synthesize and compose a great answer.
What are some examples of models that mix traditional search results with generated answers?
So there are several approaches right now to taking a traditional database of information and a large-scale language model, and either checking, cross-referencing, or using the trusted, focused corpus of information to guide the way the answers are crafted. For example, telling a system, please construct an answer only using information from this database. So an example of this kind of thing would be you have a large-scale language model trained across the web, including content from the medical literature, let's say on PubMed, that's been available for crawl. And then you're in a specific hospital that has a database of electronic health records with patients and outcomes. And you want to basically use the power of the general technology, but have it really be leveraging local data. And another approach is, of course, taking a search engine, bringing back a set of search results, traditional results, which might be copious and large, and then using the large-scale language model to weave together these results in a way that provides a beautiful summary and makes sure it's grammatically correct and flows, but gives references back to the sources. There's a technology that's referred to as RAG, or Retrieval Augmented Generation, where you actually are using a database together with a large language model. Over time, per the pressures and stresses and needs for veracity, for confirmation, for references, for attribution, we're going to see more and more work going on that combines databases of various kinds, whether it be scientific facts or dynamically retrieved information from the web, from a search engine, or hospital data that's used in a secure and private way, combined with the large-scale language models.
Thank you. So Microsoft has some AI products that don't have like a visible persona like Copilot. It's also done other products in the past, like Shell Ice, which is a spin-off that have actual personality, character, genders. So what decides whether an AI product should be more personified or not? Do they serve different needs or different markets?
In the world right now, whether it be startups or large companies or academic groups or NGOs working with these technologies, are working to find ideal uses of the technologies. We're seeing some fairly general purpose capabilities that could be applied in numerous ways, as well as focused specifically and tuned to different tasks. And the same goes for the designs of the human-computer interaction. It's a rich, important space. My team has published what we call principles for human AI collaboration, design principles, guidelines. I've worked on, over the years, principles of mixed initiative interaction. What are the best practices for how to build systems that can work with people in a fluid manner and augment them and extend them and empower them in different ways? The decision about whether to anthropomorphize and personify or have a presence that's human-like is an interesting question. Should that be done? Now, my earliest days at Microsoft included a deep interest in social user interfaces, as they were called. Some of you may remember Clippy. Well, that was partly work for my team back in those days, to create not just the quiet Bayesian inference, but to have it actually come forward and be an assistant that would be a point of focus of attention, for example, give it personality. And there's been quite a bit of research on that. At the same time, a lot of baggage can come with attempts to anthropomorphize AI systems, expectations, inappropriateness. So depending on the application, we want to be cautious about whether we want to have associate the intelligence and problem solving and capabilities and advice with an identity of some kind, or a quiet humming AI service. And I think we'll leave that to the designers and to the end users to work through over time. But one thing I know for sure about the human AI collaborative experience, I want personally to see systems built that celebrate the primacy of human agency. Human self-determination, human empowerment, human cognizance of how these tools work. Because I think these systems should always be nurturing and supporting people. And with people and their goals and their needs quite explicitly at the center.
Mm-hmm. Thank you. Okay. How can generative AI help users author and contribute content as well as retrieve it?
Well, generative AI at its core is generative. The tools certainly have long-term promise to people and to civilization as tools that could help people with composing and synthesizing and summarizing and creating. And this includes creating in the sciences, assisting people with understanding hypotheses and directions for doing experimentation and research. It includes artistry of various kinds. And in writing, it's interesting, in some ways we need to learn how to use these tools. One way that I've been using large-scale language models is to write something. I like doing my drafts. And then telling the AI system, you're an expert editor. Please look at my draft, and in angle brackets after sentences, if you think I really need to sort of make something clearer or enhance it, like an editor, and I always say you've been such an expert editor to get the system all juiced up and get the right, neurons flowing and in the right mood. Give them my draft and have the system act like an editor. I'm the writer, but I like the idea of having a system help me to compose and to think about being clearer sometimes. I think coming up with uses like that, tools and educational programs that help people use these systems to create will be very useful. And we need to keep people at the center. People are the drivers and the creators, but these systems can definitely empower and extend their abilities.
Thank you. So you co-authored a paper titled Sparks of Artificial General Intelligence that examines GPT-4 and other language models like it. Could you explain to, for one of our visitors, what your conclusions are in that paper?
In late August of 2022, my team was one of the first to gain access to GPT-4 to test it for safety and to look at its capabilities. And we were wowed by what we were seeing in terms of the jump in its power from what we had seen in the earlier version of GPT in that series. So much so that we viewed it as a phase transition. And words like polymathic came to mind. So we saw it showing powers of the kind of general intelligence people had talked about for years, creating or seeing one day in future AI systems. Now, we saw incredible abilities to compose content from different fields, to write a mathematical proof, you know, in the form of a Shakespearean poem, to bring together disparate areas of healthcare and public health, to talk about law and science and weave together coherent answers. This polymathic ability really stuck out. The ability to have the system reason about the beliefs of multiple people in a story. What does person X think about person Y, and why did this happen? Explain a theory of mind, as we refer to this, that's so central in how we work as social creatures, as humans. So in seeing these powers, what came to my mind, and I was the person who formulated that title, was not a huge leap in general intelligence, but certainly we were seeing sparks. We were seeing sparks of the kind that, with work and with more science and with more pushing and understanding and insight, could maybe extend to arcs someday, and maybe to deeper understandings. Our excitement, I think, shows in that paper, in that we went through and we spent time in a conference room that was dedicated to just studying GPT-4 for months, trying different things out, talking about them, pushing for limitations as well. Oh, this system can't plan very well. Oh, here's where it fails. Oh, that's interesting. So it wasn't a consistent, a statement that we now had something that was a breakthrough, but we saw sparks, and the sparks were certainly intriguing.
Thank you. Could you talk about your work to align AI with social values, including the partnership on AI?
The programs that I were in and the projects that I worked on over 20 years in AI, my first 20 years, were always aimed at the obviousness that this technology would be incredible. It would bring wondrous new insights and powers and accuracies, whether it be in medicine or other areas of science, in daily life, to humans. There was always a sense of, we're building a better future. But I always had in the back of my mind a sense for responsibility, that as scientists, we were responsible for all uses of these technologies, and the downstream effects, whether they be via malicious users or inadvertent, or even deeper currents of how the systems end up flowing into society and changing things. I became the president of the Maine Association of AI Scientists in 2007 for a 2-year term to 2009, and I named my presidency, or the theme of it, AI in the Open World, because we were seeing then these systems being rolled out in medicine and other areas for the first time, AI coming out. And one of the projects I kicked off was called the Presidential Panel on Long-Term AI Futures. We gathered together a set of scientists, I thought the best scientists we had in the field, who also had an angle of interest in societal influences. And we broke up into 3 different groups: short-term disruptive influences of AI, longer-term influences, including concerns about runaway AI and losing control and some of the things that people worry about these days, and then ethics and legal issues. And we came together at Asilomar in February of 2009. So interestingly, a little bit more than 15 years ago, to meet for 3 days. A fabulous meeting where we came to understandings of some concerns, some of which have come true, like criminal uses of AI, deceptive uses of AI, with some guidance for the future. 5 years after that was 2014, And I thought, things are moving pretty quickly. We need to sort of stay on this. Let's do this again. But then I thought, boy, every 5 years would probably be a good time to really rethink and provide more guidance. And my wife and I made a decision to endow Stanford to kick off a process that would take the Asilomar study and have that happen every 5 years, not for 100 years, but for as long as Stanford exists. And we call that the 100-year study to give it a name like that would capture some long-term duration. And the idea with that study is to bring together experts with a standing committee and a study group every 5 years to really provide proactive assistance and guidance to government, to academia, and to industry, and to the civil society about where are things going and what might we do to shape this for a future where we can leverage these technologies for human flourishing, and what concerns do we have about guideposts and guardrails. Shortly after launching the 100-year study, I got interested in the idea of pulling together a multi-party stakeholder approach. So if you think about this, the Asilomar study and the 100-year study at Stanford are expert studies. They bring together the top leaders in AI and the social sciences and economics. What about the rest of us? And I worked with a number of partners to co-found what's called the Partnership on AI, which is a nonprofit multi-party stakeholder group which is also looking out for the future and has really grown and matured over the last 7 years or so right now to becoming a player and a force that brings together civil society groups with the large technology companies, with smaller startups, with government agencies, and so on, to promote studies and make recommendations, whether it be on synthetic media or safety of these models and their uses and best practices, or equity issues, biases and fairness, and so on. Now at Microsoft, I have to take this home because I just felt like it was really critical for a large company getting involved with these technologies to have a sense of values and ethics and guidelines, and to reflect as an entity, because it's become a key player in the world, companies more generally. And very often we found that we were generating and building technologies that were in some ways a crashing wave ahead of regulatory activity, ahead of our government leaders and our laws. So we had to sort of be present and be engaging, and also be open and humble about what we were doing. So in 2016, working with Brad Smith, our general counsel at Microsoft, I set up what's called the Ether Committee. It's kind of an acronym for AI ethics and effects in engineering and research. And we pulled together representatives from across the whole company, as well as experts in AI, and asked the question, in fact, working with Satya Nadella, what are Microsoft's AI principles? And we came up with 6 principles that have stood the test of time. You can read about them on the web, but they guide everything we do in AI. The Ether Committee also set up a review program for sensitive uses of AI, to think through, first of all, how to define what was a sensitive use of AI, a use of AI that would need a special review with a panel of ethicists and legal people, philosophers, as well as engineers and scientists. And we came up with 3 guiding attributes of a project or an application that would mean that project would require a sensitive use review by the Sensitive Uses Committee. And these 3 attributes have stood the test of time, going now on 7 years. 1, starting at the core, does this application put any end user at risk of physical or emotional harm? 2, we'll go out on this ring, does this application put someone at risk for losing a consequential opportunity or service, like education, healthcare, or access to a loan. Going out further, does this application put Microsoft at risk to its commitment to human rights, civil society, civil liberties, privacy, democracy? Every application is considered on those three fronts, and if any of those are pinged, we have a sensitive uses review, impact statement, and an analysis. And numerous projects have gone back to the lab or have been canceled or been refined and modified based on the feedback from that committee. Now, with the standing up of foundation models, these large language models that we've been talking about today, we set up a new review project or program for any Microsoft application that ships with a foundation model. It must go through what we call our Deployment Safety Board, the DSB. I serve on the DSB, and I had hoped to see, 10, 12, 20 reviews, but it turns out it's been over 150. And it's a very busy board that's learning how to do metrics and red teaming and building up quite a capability to measure and define dimensions of risk we see in these applications, as well as benefit, and provide feedback back to the product teams that are building these systems.
Well, thank you very much.
You have the whole picture now.
So
hopefully you get like one or 2 seconds out of that would be interesting.
Yeah.
Yeah.
So what applications of chatbots and large language models today most excite you and most concern you?
I'm most excited about the use of these tools for the sciences, the biosciences, material science, for addressing key challenges in healthcare, understanding the foundations of cellular function, foundations of cancer and its mitigation, for example. Materials, the ability to generate and help scientists generate and review novel materials that could be useful in energy or in extracting carbon from the atmosphere. I think we'll see incredible breakthroughs with use of these tools to help generate and filter and compose. I'm most concerned that these tools will be used maliciously to disrupt democracy by getting in the way of an educated citizenry, by interfering with people's understandings of the world via synthesizing fake events, histories, synthesizing impersonations and persuasive content that plays on people's minds and cognition. We need to work to mitigate those possibilities. A second concern is, I would say, the deeper currents of how these systems will flow. I think we'll get great benefit out of these systems in areas like education and healthcare, and even in supercharging our democracy. But I think we have to be careful to make sure we guide it and watch it and monitor it, because these systems will have deep influences, and we might have deep currents, for example, around implications for education, independence of thinking, creativity, human authenticity, even in communications, for example.
Mm-hmm. How important is the issue of trust to the future of chatbots?
I think trust is critically important. I think these systems will have to generate well-calibrated competences and report them when they're generating facts or imagery, to share with end users with humility what they're coming up with. Overconfident systems won't be trusted. Underconfident systems will have the same challenge. So the idea of calibrating and sharing competences is a core aspect of establishing trust with end users. In the end, we're going to have to also work with people and educate them about any particular tool and how to best use it. And I like to say that the end user in the end in many fields will be the accountable agent for how they interpret and make use of what comes out of these systems. At the same time, we'd like these systems to be as good as they can possibly be with sharing their competences and, for example, leveraging tools that let them assert facts and leverage content that is verified and elsewhere.
A lot of the rhetoric about AI has swung from utopian to apocalyptic. What's your thought on this?
Is your question, you mean swung now from utopian in the past to apocalyptic now, or?
Both. Well, some people are saying that AI is going to solve all our problems. Other people are saying AI is going to destroy humanity. Others are somewhere in the middle. What's your thought on this?
I'm impressed that people are reflecting so much about the implications of artificial intelligence technologies, probably in a way that was not done given big influencers in technology like electricity or flight. So in some ways it's very healthy we're seeing a conversation because people realize there is incredible capability and many, many influences of this technology as it's being leveraged throughout society. I'm overall optimistic that, like we've come to regulate and leverage in good ways electricity and flight, telephones, and other communication apparatus technologies over the years, that we will do the same with AI. We will leverage it to benefit civilization. It'll become a contributor to our society in numerous ways. I think we have to keep our eye on it too, because it's a powerful technology. It has many, many applications. We can't necessarily point our finger right now and say it's going to be bad or good, besides saying, look, in the past we've done well with technologies. Human beings, in fact, are where we are with our inventions by our ability to understand them and wrap our civilizations around them. The language that I'm using right now to talk to you is a human invention. Isn't that amazing? That we've invented something and then we've co-evolved with it very deeply and also for our society. The same will happen with artificial intelligence. We will co-evolve with this technology. It'll become part of our everyday life. It won't be so exotic. You know, my grandmother told me once, I was walking with her, how when an airplane would fly overhead in New York City, everybody would stop and look at the sky and point and look at each other and ask themselves, what did this all mean?
Is it important to explore alternative approaches to AI beyond deep learning and large language models?
I'm a strong believer in taking a diverse and curiosity-driven approach in science, more in general, whether it be computer science, the artificial intelligence subdiscipline, or any area of scholarship. There's lots of excitement right now about this particular technology, but there's also countervailing approaches and a kind of a back and forth, and the ongoing tension between methods in AI. I've lived through and helped to drive a number of different paradigms over time. I don't expect this one to be the only one we're going to be immersed in. I think we'll be seeing quite a bit of interest and science coming out of this particular track that we're on right now. But I also see evolution happening, and I see multiple methods even now. And In many ways, we still have a constellation of approaches. The public is hearing a lot about these methods. There's been a superheating given the recent advances and the availability of these methods for people in daily life. But a lot's going on in artificial intelligence, and it will continue.
Thank you. Is Microsoft's relation with OpenAI something you can comment on?
I'll just say that OpenAI and Microsoft came together. I was at some of those first meetings to reflect about working together and collaborating, where essentially at the core of our relationship was a discovery that we had shared values about leveraging this technology for good. I think OpenAI came to Microsoft in part because of some of the values we discussed earlier. The AI principles we've had, our methods for reviewing sensitive uses of artificial intelligence technologies. It's a deep level of trust there among the companies in terms of the ultimate goals of what we're doing.
Thank you. What do you see coming in the future for large language models and for artificial intelligence more generally?
I predict that over the next 10 to 15 years, we will see some answers to my ultimate deep motivating questions that brought me to this field, which is insights about the foundations of the way our own minds work, how neurons can come together to form these incredible systems that give us everything. To me, that's the most fascinating and exciting aspect of AI, that we will likely continue to head in that direction of answering basic questions about intelligence.
Wow, thank you. Great to end on. Okay, thank you so much. This has been great.